All right, here is video 2. We're talking about the atomic structure and the periodic table. Describe the structure of an atom and including the locations of protons, neutrons, and electrons. And so we know that there is a nucleus which has which contains protons are positives and neutrons, which are neutral. All right, neutrons do not have a charge, but they do contribute to the mass because they are in the nucleus, tightly bound. And then, of course, there are electrons, and so there are orbitals, or we equate them to energy levels, those shells. And this is what contains the electrons. And so a quick diagram of that would be, of course, our nucleus in the center that has our, let's make that a little bigger, that has our protons and our neutrons. And of course, it depends on what the element is that would have how many of those. And then you get fancy and create the shell outside, right? So depending upon how many protons there are to affect how many electrons, but of course, hello. I said in the last video I like technology, and now I don't quite like it as much. There you go. And there are electrons. So that's kind of like what an atom looks like, and we talked about how to draw those in terms of our Bohr models. But we want to be able to be comfortable with knowing how these particles are related to each other. In terms of an atom, neutral atoms should have the same number of protons as electrons, and that's because neutral does represent and mean zero, net charge of zero. And so we have a couple ways to show these with our elements and our symbols. And then, of course, our actual values here. So for the first one, we see copper 63. Now, the symbol, of course, is copper. And based on magnesium down here, you see that we have two values that we need to add onto our symbol. Well, one is going to be our atomic number, and one is going to be our mass number. So I'm going to put atomic number here, and then I'm going to put mass number. And this is actually something that we're going to talk about a little bit later. Actually, you know what? Let's do it now. So we kind of want to figure out what the difference between these two things is first before we then go up and fill this out, and so we can be able to identify all of our values accurately. So when we talk about the atomic number is the identity of an element on the periodic table. In our periodic table, we have the atomic number for each element itself, which is also equal to the protons. All right, and so if we know the atomic number, we know not just what element it is, but then we also know how many protons it has. Whereas the mass number, we get an average, a weighted average mass on the periodic table. That is what our decimal numbers are. But when we talk about mass number, we're talking about a specific isotope. We'll talk about an isotope by definition a little bit more in the next question. But for the mass number, we just have to know that it is the total of the protons and neutrons within a nucleus, right? And so for our mass numbers are only ever going to be the protons plus neutrons. They're also only going to be whole numbers because we'll see how we calculate those averages the weighted averages here in a little bit. But when we write these symbols out, you'll notice that we write them as sodium hyphen and this number. And so I'm going to write out two things here. I'm going to write out sodium, and we'll do it actually above this. I'm going to write out sodium 11. And then sodium 22. And when I go to my periodic table, I identify that sodium is symbol Na. And that is atomic number 11. And so what we see here is there's two different number values after that hyphen. Well, think about what this first one is saying. This first one is saying that I have sodium 11, which, well, if we're already stating that it's sodium, this tells us the atomic number, right? So what this first version is saying is basically sodium, sodium, and we don't need to say that, right? So instead, when we write these out, the sodium is the atomic number itself, and the number that follows is the mass number for that particular isotope, right? And so that is something that we say, okay, that's why that's not correct. So both of those mean mass number. And so we can compare sodium 22 and sodium 23 because within the nucleus, so if we have Na22 nucleus and we have Na23 nucleus, well, both of those are going to have protons and neutrons inside of them. And we know that sodium is atomic number 11, which means it has 11 protons. This is sodium as well, so it's also going to have 11 protons. So the definition of an isotope is that the mass numbers are different based on the neutrons inside the nucleus with it. So there's certain elements that are able to have different neutrons in the nucleus, and that would be the total. So that would represent an isotope. So we'll define that specifically down there after we fill out the chart above. So this is effectively the difference between the atomic number, which is the proton amount, and the identity, compared to the mass number, which is the total added together. All right, so hopefully that clears that up. So coming back up here, now this is starting to make a little bit more sense to us. In terms of the element itself, copper 63, this 63 is, again, the mass number. And I know that mass is protons plus neutrons. So what I have to do is figure out what the atomic number of copper is on the periodic table, which in this case it's 29, as is all cases for copper, which means it has 29 electrons because it is a neutral atom. And then to find the number of neutrons, I just take that 63 and I subtract 29 from it. And I end up with 34 neutrons inside the nucleus there. But we are missing our values there on the symbol, excuse me, on the symbol itself. And so what we see is, especially by using magnesium as an indicator there, if you were struggling on this, that the bottom number is going to be the atomic number, so that would be the protons. And then the top number up here is going to be that mass number that we're given, so this would be 63. All right, so now let's go through the other ones. Mg is magnesium. And that would be magnesium 24 because, again, the mass number is what we put on top. This is our atomic number, which is the number of protons. So we have 12 here, which means we have 12 electrons. And, of course, neutrons aren't always going to be the same. This is a nice case where it ends up being the same as the others because 24 minus 12 is 12. All right, going through the others, uranium is U. Some of you in class were mentioning, oh, wait, I look and I see that uranium has a mass of 238.03. Why does it say 235? And remember, we are talking about isotopes, so there are different variations of uranium based on different masses because of different neutrons in that nucleus that we can have. So this is just the 235 isotope for uranium there. Uranium itself is 92 as an atomic number, which means there are 92 protons and there should be 92 electrons. And then I take the mass number, 235, minus our 92 protons, and we end up with about 143 neutrons inside that nucleus. And the last step we can do is work backwards, and we can remember that if we have protons, then we know exactly what element we're talking about because that is the identity of it. And so I look over and I see that that is chlorine, because chlorine is atomic number 17. So look how much of this I have already filled out just by looking at the proton amount. And the last step would be to figure out what the mass number is that goes here and after the hyphen. And I know that it would just be the addition of the protons and neutrons. So, and I put the arrow there, sorry, that was electrons. So protons plus neutrons. And you might be like, well, aren't protons and electrons the same? Yes, right now, but again, they change when we start talking about ions. So that's a little bit more accurate there for you. So 17 plus 18 does give us 35. So this is the chlorine 35 isotope. And we're good to go there. This next part, hopefully you have the colored periodic table in because that is going to help you a lot with how we color-coded these. The halogens are in group 17 for us, since we just numbered all of our groups in order from 1 to 18. And the halogens are, the groups, of course, are the columns. So groups go up and down. The periods go left and right. Sorry if you hear dogs doing dog things in the background. I apologize. The halogen in the fifth period, so I'm looking in group 17 and in the fifth period, so I just kind of match this up, kind of like Battleship. And we have iodine there, so I would just write I for iodine. And what's the alkaline earth metal in the second period? Alkaline earth metals, those are in group 2. So I match up group 2 with the second period here. That is going to be beryllium. And then I have the noble gas in period 1. That is group 18. We color-coded those purple. In period 1, that is, of course, going to be helium. And element with 26 protons, that one's a nice one. I don't have to measure or mass out anything. And that's going to be our iron. All right, so continuing on, what's the difference between an ion and an isotope? We'll do the color coding here again. Ions are atoms. Well, they're not atoms, actually. This is when the number of protons does not equal the number of electrons, right? And so we can have ions form because of a loss or a gain of electrons, right? Losing or gaining electrons. Now, it's important to note that it's the electrons, and I want you to remember this. Protons never change, because the protons are the identity of the element. And so if we're changing the proton amount, then that means that we're changing the identity of the element, and that is a big no-no. So an isotope is similar in terms of something's changing, but protons aren't. And in this case, that is the mass number. So an isotope is where the number of protons are actually, instead, let's do it like by a better definition there. It is a different, on the base level, different variations of atoms with different, I'm going to say atoms of, let's do the eraser here, different variations of atoms of different, or I should say, certain elements that have different mass numbers, right? And that is because neutrons change, right? Again, the protons don't. It's kind of like having a, that we know that different breeds of dogs exist, correct? And we can have dogs such as a beagle, and dogs such as a lab, which you might have heard here crunching on her bone a little bit ago. But the idea is beagles and labs do represent the same thing, right? The same species of dog, but they are different sizes, or they have different masses. And so that is an analogy that you can use to talk about isotopes, where we have elements, but we have different versions of elements. Just like there's different versions of dogs, there's different versions of certain elements that have those different mass numbers. And now, because of this, what we can do is calculate the average atomic mass of these, and those are the decimals that you see on your periodic tables. So here we have element X, which has 1, 2, 3, 4 different versions of itself. So 4 different isotopes based on the changing mass. And so we say, all right, what do we have to do? Well, our average atomic mass calculation is take the mass of isotope 1 and multiply. I'm sorry about that. They were doing so well. So the mass of isotope 1, and of course I can't pause this, so mass of isotope 1 times the percent abundance of isotope 1. All right, and so you will be given the percentages and the masses there. And then I add mass of isotope 2, mass 2 times percent 2, so on and so forth, and then we end up with having to multiply by 100. So you do that for as many isotopes as you have. And what we end up seeing is that for this particular isotope, we have a mass of 34 and a percentage for that of 52.04%, plus our next one, which is 36 times 22.96, plus 22.9, there we go, and then 37 times 2.28, and 38 times 22.72. All right, and then all of that added together, and then you divide by 100. And so what this looks like, if you want to do it all at once in the calculator, you can take your parentheses, that's why I use parentheses there, 34 times our 52.04 plus 36 times 22.96 plus 37 times 2.28 plus 38 times 22.72. All right, we get a value. So this effectively comes out to be 3,543.64, and then divided by 100 to get our actual value there. And then what you'll end up seeing is that it's really just moving the decimal back 2 places. You can go here, fraction. Oh, it's already in a fraction and a math decimal. And we get the 35.43. So just to show you, to confirm there, 35.436, which I'm going to bump that 3 up to a 4. And we say AMU for atomic mass units for this element that is unknown, right? It's unknown element X. But that would be its mass on average right here. right? So there is the way that we can calculate all of those values on the, whoops. Oh, well. There we go. It does not like the end of that screen. There we go. Just to move it over a little bit. So that's how we can identify those average atomic mass units that we see on the periodic table. Those are all weighted averages, kind of like the way that your grades are calculated and other things like that. All right, so I'm actually going to go through the electron configuration portion now. The electron configuration is something that we did in class, where we use the periodic table to then identify where those electrons that we were talking about that exist in those shells, right, or in those energy levels and those orbitals, where they actually are based on energy level. And so writing the complete electron configuration is based on using that and identifying that we have one. If we go over here, krypton, we always have to start with our first element, which is hydrogen. That is our 1s1. Then we continue on. We've blocked off our periodic tables, and all we have to do is fill in those orbitals in order as we go. So for krypton, we start with 1s2. That represents hydrogen and helium. We have 2s2, lithium, beryllium. We have 2p6, that is boron all the way to neon. 3s2, that is sodium to magnesium. We then have 3p6, which is aluminum to argon. We have 4s2, that is potassium to calcium. And then we go to the first set of transition metals, which are part of our D block. And we said that Ds are delayed. So although they come after the 4s orbital or subshell, we actually have a 3 in front of the D block because they are delayed in energy level. So all of those electrons are actually going backwards into the third energy level. And then once we exit after zinc, we end up back into the fourth energy level in the P subblock. So the S's and the P's are always in line with the period that they're a part of, which is their energy level. The D's are delayed by 1 period. And if we were to do the F orbitals, those would be delayed twice, but we don't get into those. So then we see that krypton is in the 4p's, and it's actually the last one. And if I count from gallium, that gets me to that 4p6, and I know that 4p6 configurations are what the noble gases end on there. In terms of magnesium, this one's going to be a little bit quicker because we just have to end at 3s2. And so I put all of my values in going through 2p6, 3s2, and that's where my magnesium would end. And before I wrap this video up, because the dogs are getting a little stir crazy, and I apologize again, but by looking at our periodic table, we kind of show this where our S blocks are in the blue, our P blocks are all of those in the on the right side there. Helium is a part of the S block in theory, right? Because this periodic table is just looking like this for aesthetics. So and then we went through, we see this is 1s1, this is 1s2, and then this is 2s1, 2s2. 2p1, 2p2, and so on and so forth. And so we keep going, and we can identify where our elements need to end at for our full configuration. So in the next video, we will continue with the electron configuration idea, and then also incorporate our abbreviated values. So I hope this video helped, and part 2 is now part 2.5. Or part 2.5 is going to be coming soon. All right, take care.